This is a continuation of our lecture on sets, a continuation of lecture 2. We left off at definition 9 and we will resume at definition 9. Definition 9. The Cartesian product of sets A1 through AN is denoted by A1 cross A2 cross AN is the set of ordered n-tuples where we have the n-tuple A1 through AN, where A subscript I belongs to set A subscript I for I equal 1 to n. In other words, A1 cross A2 cross to AN is the set consisting of elements that are n-tuples A1 through AN, where A sub I is an element of set A sub I for I equal 1 to n. Example 19. What is the Cartesian product A cross B cross C, where A is the set 0, 1, B is the set 1, 2, and C is the set 0, 1, 2. The Cartesian product A cross B cross C consists of all ordered triples A, B, C, where A is an element of A, B is an element of B, and C is an element of C. Hence, A cross B cross C is equal to 0, 1, 0, 0, 1, 1, 0, 1, 2, 0, 2, 0, 0, 2, 1, 0, 2, 2, 1, 1, 0, triple 1, 1, 1, 2, 1, 2, 0, 1, 2, 1, and 1, 2, 2. Note that when A, B, and C are sets, the quantity A cross B cross C is not the same as A cross B cross C. Remark. We use the notation A squared to note A cross B, the Cartesian product of the set A with itself. Similarly, A cubed is equal to A cross A cross A, and A to the fourth power is A cross A cross A cross A, and so on. More generally, we have A to the nth power consists of n tuples, A1 through n, where A sub I is an element of A for I equal 1 to n. Example 20. Suppose that A is equal to 1, 2. It follows that A squared is equal to 1, 1, 1, 2, 2, 1, and 2, 2. And A cubed is equal to A triple 1, 1, 1, 2, 1, 2, 1, 1, 2, 2, 2, 1, 1, 2, 1, 2, 2, 2, 1, and triple 2. Relations. A subset R of the Cartesian product A cross B is called a relation from the set A to the set B. The elements of R are ordered pairs, where the first element belongs to set A and the second element belongs to set B. For example, R is equal to the set A0, A1, A3, B1, B2, C0, C2 is a relation from the set ABC to the set 0, 1, 2, 3. A relation from a set A to itself is called a relation on A. Example 221. What are the ordered pairs in the less than or equal to relation which contains AB if A is less than B on the set 0, 1, 2, 3? The ordered pair AB belongs to R if and only if both A and B belong to 0, 1, 2, 3 and A is less than or equal to B. Consequently, the ordered pairs in R are 0, 0, 0, 2, 0, 3, 1, 1, 1, 2, 1, 3, 2, 2, and 2, 3, and 3, 3. Note that in every case, the first element of the tuple is less than or equal to the second element of the tuple. Using set notation with quantifiers. Sets can be used to restrict the domain of a quantified statement. For example, for all x, element of S of P of x denotes the universal instantiation of P of x over all elements of the set S. In other words, for all x, element S of P of x is shorthand for all x, an element S if implies P of x. In a similar way, there exists x, an element S of P of x denotes the existential quantification of P of x over all elements in S. That is, there exists X, an element of S of P of X is shorthand for there exists X, X is an element of S, and P of X. Example 22.1. What does the statement for all X, an element of the reals, X squared greater than 0 means? The statement for all X, an element of reals, X squared is greater than or equal states that for every number X, X squared is greater than or equal to 0. The statement can be expressed as the square of every real number is non-negative. This is a true statement. Example 22.2. What does the statement there exists X, an element of the integers, X squared equal 1 mean? The statement there exists X, X an element of the integers, X squared equal 1 states that there exists an integer X such that X squared equal 1. This statement can be expressed as there is an integer whose square is 1. This is also a true statement because X equal 1 such an integer as is minus 1. Truth sets and quantifiers. Given a predicate P and a domain D, we define the truth set of P to be the set of elements X in D for which P of X is true. The truth set of P of X is denoted by X is an element D and P of X. Example 23.1. What is the true set of the predicate P of X where the domain is the set of integers and P of X is the absolute value of X is 1? Solution. The truth set of P, X is an element of the integers, the absolute value of X is equal to 1 is a set of integers for which absolute value of X is 1. Because the absolute value of X is equal to 1, X is equal to 1 or minus 1, and for no other integers, we see that the true set of P is a set minus 1, 1. Example 23.2. What is the true set of the predicate Q of X where the domain of the set is integers and Q of X is equal to X squared equal 2? The true set of Q, X is an element of the integers, X squared equal 2, is a set of integers for which X squared equal 2. This is the empty set because there are no integers X for which X squared equal 2. Example 23.3. What is the true set of the predicate R of X where the domain of set of integers R of X and the absolute value of X is equal to X? The true set of R, X an element of Z, the absolute value of X is equal to X, is a set of integers for which the absolute value of X is equal to X. Because the value of absolute X is equal to X if and only if X is greater than or equal to 0, it follows that the true set of R is in the set of non-negative integers. Here are some example exercises that are similar to the exercises that are assigned to you. Use set builder notation to give a description of each of these sets. The set 0, 4, 8, 12, and 16. The set builder numeration would be 4n, and where n is an element of the integers, and n is and 0 is less than or equal to n less than or equal to 4. Note that the comma in this case means and. Case B, or part B, -1, 0, 1, x, where x is an element of the integers, and x and 1, -1 is less than or equal to x, less than or equal to 1. A, B, C, D, x, where x is an element of the lowercase English alphabet, and A is less than or equal to x is less than or equal to D. For each of these pairs of sets, determine whether the first is a subset of the second a subset of the first, or neither is a subset of each other. A, the set of airline flights from New York to New Delhi. B, the set of nonstop airline flights from New York to New Delhi. B is a subset of A. B, the set of people who speak English. The set of people who speak Chinese. Neither. C, the set of flying squirrels or the set of living creatures that fly. A is a subset of B. 9. Determine whether these statements are true or false. A. 0 is an element of the empty set. No. B. The empty set is an element of the set containing 0. No. C. The set containing 0 is a proper subset of the empty set. No. The empty set is a proper subset of the set containing 0. Yes, every element is the set. Every element on the set on the left, vacuously, an element of the set on the right, and the set on the right contains an element, namely 0, that is not a set on the left. 0 is an element of the set containing 0. No, the set on the right has only one element, naming the number 0, not the set containing the number 0. The set containing 0 is a proper subset of the set containing 0. For one set to be a proper set to the other, the two sets cannot be equal. The set containing the empty set is a proper subset of the set containing the empty set. Every set is a subset of itself. Yes. 16. Use a Venn diagram to illustrate the relationship that A is a proper subset of B and B is a proper subset of C. We see that we have the rectangle of the universe. We put A as a circle in the middle here and surrounded by the other two sets. We put B as including all of A and at least one element which we have named lowercase b. We enclose both A and B in C and include at least one element lowercase c that is not in B and not in A. This concludes this lecture.